Good morning. Thanks to the organizers. Pleasure to be here. What I would like to do today is go through our, I would say by now, a comprehensive approach to the question of operational limits of machines. And notice that I say machines rather than heat machines or heat engines, because that's the crux of what I'll be talking about. In many cases, we don't deal with heat machines properly, and therefore their operational bounds are different than what we're used to. Okay, but I will emphasize the fact that it is not really the difference between quantum and classical operational principles which is behind it, but other principles which are fully consistent with thermodynamics. I would like to mention my co-workers. Wolfgang Niedenzu has been very prominent in what I'll be talking about. Of course, in earlier work, which I'll mention, I had as collaborator David Gelbwasser, a wonderful student at that time. Among my collaborators, I would like to mention Marlon Scully, who has been not just a mentor, but also a basically lifelong collaborator of mine on some of what I'll be talking about. So, where's the forward? Shift or what? I don't know. Oh, just here. Sorry. Okay. So it's quite remarkable that the same principles exactly apply to a steam engine and an atom, okay, when it comes to heat engines, all right, which inevitably consist. So, Marlon, you missed my acknowledgement of yourself, but that's... Do it again. Yeah. All right. So what we must have in a heat engine setting is two baths, the energizing hot bath and a cold bath where you dump your entropy, a working fluid, and a piston. Okay, those are which is used to extract the work. Now, those are essential ingredients, and the working fluid, as I emphasized, can be either a steam engine or an elementary quantum system, an atom or what have you. And in all of these cases, you are restricted by the Carnot bound, which tells us that the maximum work extractable over the heat input cannot exceed 1 minus the ratio of the two bath temperatures. And this is a direct consequence of the second law, which in which we can attain the Carnot limit when the engine operates reversibly, okay? And by reversibly, we mean that there is no entropy production in this engine. So, having said that, does this mean that quantumness cannot help us change the rules of the game? So this question has arisen in the context of quite a few works in recent years. Okay, is it possible to increase the efficiency of heat engines beyond the Carnot bound? And this is what I'll be referring to. Okay, so the pioneer in this field was Marlin, who in 2003 with his co-workers showed that if you take a Carnot engine and you feed it as an energizing source, not with ordinary, say, two-level atoms, but instead by atoms which are prepared in a superposition of two low-lying states that are nearly degenerate, then, depending on the phase of this superposition, you may achieve different temperatures, including temperatures that exceed what you would have in the absence of this coherence. And then, according to the Carnot bound, you have higher efficiency, okay? So you may essentially manipulate the hot bath temperature by introducing an appropriate phase of the superposition. Now, if you analyze this scenario, it turns out that this is a bona fide heat engine, okay? And the fact that you get here different temperatures than what you would expect in the absence of coherence in no way violates any principle of thermodynamics. But then there was a more recent claim, which I find completely intriguing, by Eric Lutz and co-workers, in which instead of feeding your machine with such, I would say, equivalently thermal source, you feed it with a squeezed thermal source, okay? And then if you attribute the increase in energy, in input energy, to extra heat, which is generated by this squeezing source, you again may exceed the Carnot efficiency as we know it. And the question is whether these two scenarios are equivalent in some sense, okay? The answer is no. I am pleased to tell you that there is now an experimental demonstration of using a squeeze source to energize a machine, but they did not really consider the issue of efficiency there. Anyway, what does this amount to? It amounts to the question whether the condition of reversibility imposed by the second law, or the absence of entropy production, holds for engines that are fueled by non-thermal baths, such as a squeezed bath. Okay, it's more general than that. And for that, we have to revisit the basic definitions, okay, of what is heat and what is work. Here, the pioneering article was due to our chairman, Robert, that in '79 introduced the distinction between heat and work as follows. Heat is associated, or a heat exchange rather, between the bath and the system is associated with the derivative of the state of the system, okay, integrated over the time interval in question, and h is whatever Hamiltonian is driving it, whereas work is keeping the state as it is, but varying the Hamiltonian. So this, of course, is very intuitive because you associate work with a force which is exerted on the system. And in fact, this corresponds to a completely unitary process. But then, as you'll see, one should take a closer look at this part, which is attributed to heat. And for that, consider a very simple example. Suppose I prepare a cavity field in a coherent state, okay? The outside is empty, so it's a zero temperature bath. Now you let this field leak out of the cavity, okay? By the end of this process, the cavity is empty, and according to the definition which associates heat with a change in the state of the system, there has been considerable change. Yes, the energy has gone from what corresponds to this alpha naught to zero. But this change is purely unitary, okay? And it has generated no entropy. So the question is whether it's appropriate to call such a process heat exchange, okay? And of course, there are numerous examples of that. Take a two-level atom which decays from an excited to a ground state. The same is true there. By the end of the process, you are in the ground state, so you are still in a pure state. The energy has changed, but entropy has not increased as we understand it. So is this heat? Well, it is according to, so this is it. It is if you don't make the distinction between what we call passive and non-passive states. Only the distinction between a passive state, which is incapable of producing work, okay, and a non-passive state can explain this difference between energy exchange and entropy change. So what are, for those that are unfamiliar, what are passive versus non-passive states? It's best illustrated by this example. Robert introduced the notion of a quantum battery. So suppose that this quantum battery corresponds to a state which is partly non-passive, okay? The green part of its energy is non-passive. It can light a bulb in a cyclic process, but if it were passive, it would not be able to light a bulb. If it were completely non-passive, it would light the bulb much brighter than that. So the work content of a non-passive state is non-zero, whereas that of the passive state is zero. And our main contention is that one should only look at the entropy which is associated with the passive state counterpart of the state that we're given. And this choice is unique. To any state, there uniquely corresponds a passive state, okay? And this passive state is reached by a unitary transformation of the non-passive state. So they both have the same entropy, okay? Why is this important? Because if you consider the energy which is exchanged between the system and the bath, you can now decompose what previously Robert called heat into two parts, one of which I would say is genuine heat, okay? And that's the part which corresponds to the change in the passive energy of the system, and a part which corresponds to the change in the work content of the system, or what we call ergotropy, or some call ergotropy. And for entropy production, only this part is relevant, where pi is the passive state that corresponds to the actual non-passive state that we have. Okay? If we now look at entropy change, then we have Spohn's inequality, which by consensus is the same as the second law. Sporn's inequality tells us that the change in the system entropy, all right, is bounded by the total energy it exchanges with the bath over the temperature of the bath. And indeed, this inequality is formally valid no matter what, assuming that the process is a Markovian process, so the bath temperature remains constant, and you can attribute the entropy change only to the system. But if you look at this total energy exchange and you decompose it into what we now identify as genuine heat and the work exchange with the bath, or ergotropy exchange with the bath, then you see that this bound may be very misleading. It's valid, but it is very misleading in the sense that if there is no genuine heat exchange, only work exchange, there is no point to identify this with entropy change, you see? So, this is our main contention, that Sporn's inequality should be replaced by such tighter bound, okay, in which the entropy change is only bounded, is only binding the change in genuine heat, okay, that arises during this process, okay? And this can be much, much tighter than Sporn's bound, and this has very strong consequences. So even if the system is driven by a time-dependent Hamiltonian, what I said is still valid. You may still identify what we call genuine entropy change with this epsilon prime, which is the energy exchange with the bath under the driving Hamiltonian, but with the condition that the initial state of the system is passive. So you first perform a unitary transformation that takes you from your actual state to the passive state, and then you use this as the initial condition for describing the energy exchange with the bath, and only that should be bounded by your entropy change. Now, intriguingly, the same is true for non-thermal baths, because imagine that you have a squeezed bath which acts on your system. It's been known for a long time that the state of the system, which is coupled to a squeezed bath, is equivalent to a squeezed to the state of a squeezed system, which is coupled to a thermal bath with the corresponding temperature. Yes. So since by a unitary transformation, how much time do we?
It's over 15 minutes.
Okay. So since a unitary transformation that takes the system from from its current state to a squeeze state has the same entropy, okay, it's a unitary transformation, then you have the same entropy bound that describes the energy exchange between the system and the squeeze bath. So you see the logic. You apply a unitary transformation which instead of squeezing the bath, yes, squeezes the system, okay, and then you let the squeezed system interact with the thermal bath. Both are bounded by the same entropy change. So the same inequality applies to the interaction of systems with non-thermal as well as thermal baths, okay? And now comes the, I would say, dramatic consequence of using this inequality instead of Spohn's inequality. Spohn's inequality, as a reminder, restricts the entropy change by the change of the total energy of the system, which includes not just the passive energy changes here, but also the non-passive part. And we get rid of the passive part, so of the non-passive part. So if you apply Spohn's inequality and you claim that the maximum efficiency of an engine is given by the absence of entropy production, i.e. you set the left side of the inequality to be zero, but you use here the total energy exchange with the system, you can get nonsensical results. And one such result was given by Parondo that got, as a result, an efficiency bound which is larger than unity. And of course, an efficiency bound larger than unity is a violation of energy conservation, okay? But he still has it in his paper. And that's a direct consequence of treating the interaction of the system with a non-thermal bath as if it were a thermal bath and using Spohn's inequality there, okay? So one should not do that. This is the, I would say, most generic setup one can consider for the purpose of this discussion. An engine where you are coupled to a non-thermal bath that has some temperature TH, but even that is not essential. But it has a non-thermal component to it, squeezing, for example. And there can be also a time-dependent Hamiltonian acting on the system, on the working fluid. You extract the work by a unitary process, by a piston, and you dump the remaining energy into the cold bath, okay? So what we get as a result of our modified inequality is the following bound, which I claim is completely universal, and that is 1 minus the ratio of the bath temperatures times the ratio of the actual heat exchange with the bath over the energy exchange with the bath, okay? Now, first of all, this, if defined properly, can never exceed unity, as opposed to what you have in Parondo's case, where you use, instead of actual heat, you use the full energy. It may have the wrong sign, and then you get this efficiency bound which exceeds 1, which is, of course, not legitimate. But what is important is that this bound interpolates between the bound of a heat engine, okay, that's the Carnot bound. That's what happens when the entire energy exchange with the bath is heat, okay, then this becomes 1. And the case where, in fact, you have all the, no energy associated with heat, okay? All that you get from the bath is ergotropy due to squeezing, say, and then this becomes 0, and the efficiency becomes 1, i.e. the engine then acts as if it were a mechanical engine, okay? It converts work received from the bath into extracted work. This is the illustration of this bound as a function of the squeezing parameter of the bath. Okay, as you see that when squeezing becomes appreciable, you start exceeding the Carnot bound. Okay, this is the actual efficiency bound which we get, but it never exceeds 1. It becomes essentially 1 when the squeezing is large, whereas if you apply the Sporn inequality, then you may well exceed unity. Okay. So I would say that this for us embeds all forms of engines in a unified framework which applies no matter what the energizing source is and what the driving Hamiltonian is. So what actually limits the efficiency? It is the condition that whatever ergotropy you get from the bath, you extract, okay, and you don't let it go into the cold bath because that's unnecessary loss. Yes, you whatever you get from the energizing bath, you should utilize as fast as possible, and whatever goes to the cold bath is just the heat which is associated with the actual temperature and inevitable entropy change, which corresponds to heat exchange. Okay, so instead of reversibility, the condition for maximum efficiency is minimal loss. Okay, minimal loss under the restrictions which are imposed by the bath. So how much time?
10 minutes.
10 minutes, all right. So now let's consider examples in which these resources that I identified, heat exchange and ergotropy exchange, play a role. So with our Turkish collaborators, we looked at the situation which Marlon previously examined for his phasonium case, but instead of letting single atom cross a Micromaser cavity and feed the cavity mode with, I would remind you, enhanced temperature, we now send pairs of atoms prepared in an entangled state, okay, such as GG plus EE, okay? And what you find then, that instead of feeding heat into the cavity, you actually feed squeezing into the cavity, okay? And in fact, very high squeezing. When you are close to this state, ideally, then what you get is a giant squeezing which you cannot achieve by other means currently. And this means that you are, in fact, in the limit where ergotropy, okay, is exchanged between your effective bath and your system or your working fluid, and you may expect efficiencies which reach unity in this scenario. But if you consider a somewhat different state, a state, again, of a pair of atoms which is prepared in a singly excited superposition of one atom being excited and the other not excited, then you may have a completely different situation in which you only exchange heat with the cavity, but the temperature which the cavity attains as a result of such an interaction can have an extremely large range of variations, which you can see here. The cavity temperature can become, this is the inverse temperature, so the cavity temperature can become essentially infinite when you feed the cavity with bright entangled states of these two atoms, and it can go down to zero regardless of what the outside temperature is. It can go down to zero when instead you have a dark entangled state, an antisymmetric superposition of these two. And since this is something which I used to do for my living 30 years ago, I know that, in fact, it is very easy to control the production of bright or dark entangled states of atom pairs. You just have to excite your molecule to the appropriate state. When the state of the molecule is ungerade, okay, it corresponds to a bright entangled state. And when the state is gerade in chemical parlance, then it is a dark state, all right? So you can really have a large variability. How much time?
6 minutes.
6 minutes, all right. So in a paper which came out these days in PNAS, it's a collaboration with Luis Davidovich, we examined the question whether in order to take advantage of ergotropy, one really needs a non-thermal bath, okay? This is the scenario I was showing you before, a non-thermal, say, squeezed bath, which feeds you with both heat and ergotropy, and you extract work from the combination of the two. But we instead looked at a situation in which you have a thermal bath, but your pump introduces ergotropy into the system. And this can be relatively easily done by passing a pump laser through a Chi2 medium and thereby squeezing the output, which is then fed into a cavity where the source of energy is just a regular thermal bath, okay? When you have this situation, you have to subtract the actual work input introduced by the pump. Otherwise, it would be unfair, right? You are putting in work from the pump. So you should do that. Yes, you subtract the work extracted, the work introduced by the pump from the extracted work, and you divide by the heat input. And then you are bounded by the Carnot bound, but you can very strongly enhance the power which you produce by this device, and you can see it here. This is the power in the presence of squeezing, just a little bit of squeezing, compared to what you have in the absence of squeezing. And so we call this catalysis of heat to work conversion. The role of the squeezing pump here is to actually make the state of the working fluid squeezed. That's the result of the action of the pump, and thereby much more susceptible to work production than if you have, say, a coherent state. That's when there is no squeezing, okay? So this, I would say, is a more economical and probably more practical way of using squeezing as a resource. Yes, not as a direct source of ergotropy from the bath, but instead as a modification of the state of the working fluid in order to make the engine operate better. So I guess I have exhausted my time, right? So let me then summarize. What I've shown mainly is the need to reconsider the first law of thermodynamics, which distinguishes between heat and work in energy exchange between a system and a bath. So we identify heat only with the fraction of the energy that yields entropy change. And to this distinction corresponds a new inequality on the entropy change, which is not the one that you obtain from the second law, okay? The second law is not enough to obtain this inequality. You have to consider the difference between passive and non-passive states, okay, which is not under the umbrella of the second law, okay? So it's beyond the second law, if you like, okay? And so this is this distinction. And then from this new inequality, you get a bound on the efficiency of arbitrary engines, which we refer to as quantum engines, but the question of their quantumness, I would say, requires further examination. And this maximum efficiency is bounded by the minimal loss condition, the minimal loss of energy which is dumped into the cold bath. So no reversibility in the traditional sense of the Carnot is required. So concerning quantumness, the appropriate questions as we see them are, does traditional thermodynamics hold for quantum machines? Absolutely yes. Are there advantages to machines that have quantum resources? I would say yes, provided they change either the passivity of the system or its effective temperature and entropy. And these are the examples that some of which I have discussed here, squeezing either of the bath but also of the working fluid, which can catalyze the power production. And there are other features which one could discuss, but they all show us that it's not the actual quantumness, but it's the ability of quantumness to change thermodynamic resources, yes, which is relevant to the discussion of engines in general. Thank you very much for your attention.
Can I go back to your battery, passive and
Yes.
non-passive? Can I think of a battery as a capacitor and
yeah.
energy Q squared over capacitance?
Yes.
For the moment. And then how do you characterize that as partly passive, partly not?
Well, I think that in terms of capacitance, you won't see the difference. So you need this extra requirement that the part which can be extracted as work, okay, is the non-passive part. So I would say that you need to go beyond that analysis. Yes?
It's a pity that you were not there yesterday when I gave my talk, because I was wondering about...
I'm sure it was.
You know, I was showing that if you have other class, not a thermal reservoir, but other class of reservoirs or resource, what is relevant is the free energy. And in different limits of interaction, you can get master equation, and you realize that the entropy production is not given by the Spohn inequality. And so maybe that's an equivalent way to look at it, but which makes contact with the concept of free energy.
Okay, so free energy is a very restrictive concept. That is why we do not resort to it. Free energy, strictly speaking, only refers to equilibrium situations, okay? To have general time dependence, as we do here, okay, would not be really consistent with free energy.
It's not equilibrium free energy, it's non-equilibrium free energy. Energy minus entropy.
But it still corresponds to some kind of stationarity, doesn't it?
Okay, maybe we can discuss.
To my knowledge. But otherwise it may be equivalent.
Maybe the last
Yeah.
question.
Oh, sorry. Yes, Eric, yes.
I have a question concerning the definition of the efficiency that you gave on page 18. For me, efficiency is defined as the output divided by the input. But if you follow that philosophy, you would add the pump contribution to the denominator and not subtract it from the numerator. So
Well, if you do that, you may violate Carnot, actually. If yes, what this is, you're talking about our squeezed pump.
No, yeah,
The squeezed pump, yes. Yeah. So I would say that to be on the conservative side, we subtract I would say the direct work input of the pump. Okay, what you are talking is the input in the sense of energy. Okay, but yeah, I mean, you know, the total energy. I mean, what we're trying to single out is the contribution of the pump not to the direct work extraction, but to the state of the working fluid, which then can be used to generate work output. So in this respect, I'm aware that there is a bit of, you may say, ambiguity there. You may either put it in the denominator or just subtract it. Fine. But if you do, then, you know, it becomes a bit strange. Why is it that having still a heat bath as your energy source, you are getting above Carnot? Okay, that's the discussion which we wanted to avoid. So we're saying, let's take the worst case. Let's just remove completely the direct contribution of the pump, and you still get a very interesting effect, which is dominant. Suppose that the actual work input by the pump is really very small. The effect which you get can still be huge. You see, that's the surprise. But thank you. Yes.
We can continue the break, so we have.
Thank you.